2. And so as a motivating example, so let's look at what we did last time. And so just look at this example of universities. So example, 2 grants and 3 universities, and just briefly repeat what we did. Universities. So the example was we have a joint probability, so 2 grants awarded to 2 universities, so X, so number of grants to 1 university, call it N, New York University, Y, number of grants to say C, California, right? So in the picture was that we have a joint probability. So he has here, we have say X, here we have Y, 0, 1, 2, 0, 1, 2, and joint probabilities was 1/9. So 1/9, 1/9. So these are the outcomes which are determined. So if 0 to X, 0 to New York University, and 2 to California University, so just one outcome. All others have a probability 2/9. So it's 2 outcomes that results in this particular combination of X and Y. And other there was 0, 0. So here was 0. So this was joint PMF, right? So joint PMF. Right? And after that we said, okay, so we can, from the joint PMF, we can calculate the conditional PMF. We need to choose which is a kind of, which is a dependent variable, so which is not dependent. And so meaning, so which we will treat as known, kind of as an observed, and then which we treat something which is still not known. So let us, previously we said, say Y is known and X is not yet known. So let us do other examples. So, so conditional PMF, and the condition here will be that, so here will be P Y given X. So Y and X is given here. And also kind of it's the same table, but with different numbers. So we have Y, X, here 0, 1, 2, 0, 1, 2. But now we're saying kind of we know that X kind of say equal to 0. And we know the realization of X. And after that we are saying, okay, so we know that now within the first row of the original table, but we'll need to normalize the number so that we sum to 1. So, and we will get in this case 1/4, 1/2, 1/4. So we do 1/9, 2/9, 1/9 by the coefficient, which was equal to 4/9, and get these numbers. And we can do it with this with every row, right? So we'll get here 1/2, 1/2, 0, and here we'll get 1, 0, 0. Right? So this is a conditional PMF. Also, kind of we can remember. So this is probability of Y. Right? It's probability of Y given that we know something. Right? So what was unconditional probability? Unconditional, unconditional, PMF of Y. Right? So in other words, it's non-conditional, the same as a marginal. It's a marginal PMF. So marginal. Okay, so right. So okay, so marginal probability. So hopefully you still can hear me. So marginal PMF of Y. Right? And this was okay. So here we have just Y's, the possible values of y's, which are 0, 1, 2, and this is just sums of the columns, right? So this was py of y, right? And it's here, it's equal to 4/9, 4/9, and 1/9. So this is just sum of the original joint PMFs, joint probabilities. We are summing along the columns here. Right? So, and then we'll get 4/9, 4/9, and 1/9. And if you compare this with the unconditional PMF, it's different from the conditional. And the conditional, they are kind of very different. So one conditional probability given that x is equal to 0, it's 1/4, 1/2, 1/4. It's different from the marginal one. And it's different from other conditional probabilities, right? So it's different from 1/2 and 1/2 and 0. So kind of in this situation shows that there is a dependence, right? If you know something about x, you know something about you, kind of this gives you information about y. Right? So if you know that there was 2 grants awarded to New York University, right? So you know exactly what's the kind of probability of the outcomes for y. So what's the number of grants awarded to the California University? This is extreme example, right? So in this case, you know that's 0, the value of x. But it's kind of a general kind of, you see that knowledge of x gives you some kind of information about y. Right? So this is a kind of dependence. Right? So this is dependence. So in this example, we observe that there is a dependence of y on x. So which is kind of conditional PMF of y depends on x, right? So you can see there is dependence here. So this is different for different x, and different from py of y, from marginal. Right? So for marginal. And so now if you want to exclude this situation, this will be called independence, right? So it's more convenient to work with kind of slightly different definition, which kind of doesn't separate y and x. Right? So some definition such that y and x would be treated similarly. So it's not immediately obvious that if y is independent of x, then it's also x independent of y, but it's true, kind of, right? So it can be checked that this is true, and well, kind of we want a symmetric definition, right? So definition is that says that well, here 2 random variables, but could be generalized. So 2 random variables, x and y are independent. Right? They're independent if joint PMF, so x and y, so this is joint PMF, is equal to the product of the marginal PMF. So px of x, px of y. So this is the definition of this thing, and let us kind of check that it's similar to what. So this is corresponds to what I said, that if it's 2 random variables are independent, that it means that conditional probability is the same as the marginal. Right? Maybe before that it's saying, so what it means actually, so what it's kind of, if you think about this, that it means that the that events, so kind of events x is equal to x and y is equal to y are independent. So this is how to relate to what we talked before. And we talked about independence of events, right? So here we're talking about independence of random variables. So to connect it, it's kind of events x equal to x and y to y are independent, but it should be independent for every x and y. Dependent for every x and y. So it's not totally new kind of things. It's just kind of, it's much more conditions. And before that, independence of events, we just needed to check one, that the product of that the one probability is equal to the product of two other probabilities. Here, well, in principle, we need to check much more kind of conditions, that there is independence for every x and y. So x and y can be infinite number of them. So potentially, we need to check infinite number of conditions. And, but again, so this is definition, and so let's look at the conditional. So conditional. Say let's look at that conditional of y given x, like in previous example. Right? Y given x. Right? So okay, so we want to calculate it, right? And show that it's the same as the marginal, doesn't depend on x. And so we do it by definition of a conditional probability mass function. We write that this is equal to, okay, so it's p joint, so pxy of xy divided by the marginal probability of the conditional, p x of x. So here's conditional x, so in the denominator we'll have a x variable. And then after that, okay, so by definition of independence, the numerator factors, so we'll have a px of x multiplied by py of y. Right, we'll need divided px of x, so kind of this is cancel out, so we'll have a py of y. And so that means that conditional probability is always equal to the marginal one, kind of, and it doesn't depend on x. Right? So this kind of the marginal was always the same, it doesn't depend on x. So this is a definition and independence and the meaning. The meaning is, well, kind of observation of one random variable doesn't say you anything about the probabilities of the outcomes of another random variable. And so now, in this example, in this particular example, we see that this is kind of this example of universities and grants. We see that they are not independent. Right? So this random variable in this example are not independent, also kind of so not independent random variables are called dependent. Kind of this is kind of nature called dependent. So kind of so if the definition of dependent is not independent. Okay, so now kind of what's the example of random variables which are independent? So now the simplest example is just to look at the kind of when we toss a die or we toss a coin. So in this case, say, let us say in this example, when we toss two dice, experiment is toss two dice, and all outcomes are equally probable. So which means that we have a probability that the outcome is 1, right? So so it's equal to the probability that the outcome is say 1, 2, right? It's equal and so on is equal to the probability. So this is kind of probability. This is here is outcomes, right? So the outcomes of experiments, not kind of random variables, but so it's equal probability that the outcome is equal to say 6, 6, kind of, right? So all of them are the same, and so total number of outcomes is equal to 36. So this is equal to 1 divided by 36. So now, and in this case, say x is a number on the first die, and y number on the second die. And so now, well, this is, in this case, we have a similar table. Right? So, but in this case, so we have a, okay, so here's a x, so x, maybe x here, y here, like before. So here we have a, right, y can be equal to 0, sorry, it can be equal to 0, so it can be equal to 1, 2, 3, 4, 5, 6. X could be also 1, 2, 3, 4, 5, 6. Right, and the probabilities are kind of 136, so probability are pretty tedious. 136, 136, 136, right, and so on. Kind of everywhere is 136. And so pretty dull table. Right? So kind of maybe not write everything, right? So pretty not very interesting kind of table. But if you look at this table, right, 1 divided by 36, right? So if you look at this table around kind of what's the marginal probabilities, right? So of x and y. So okay, so it's 1/6. So marginal probability is 1/6, 1/6, 1/6, 1/6. So 1/6 and 1/6. And so kind of this is, so and then kind of 1/6 here. Right? So it's the sum of the rows and sum of the columns. Now, and well, of course, in this case, the entry kind of 136 is equal to the product of these two things. So kind of in this case, you can see from the definition that these random variables are independent. So x and y are independent, because kind of probability that x is equal to, say, k, and so maybe x small, and y is equal to y small, is equal to 1 divided by 36, always is equal to the probability that x is equal to x small, probability that y is equal to y small, which is equal to 1/6 multiplied by 1/6 for all x and y. So kind of this is a clear kind of so tedious but clear example of what it means to be independent and kind of. And it turns out that actually in the modeling, for modeling purposes, it usually goes our way around. We have some intuitive meaning that two things are independent. So it happens in the real life that the two things, and we think that they are more or less independent. Nothing is really kind of, or there is always some dependence between things, but approximately independent. And we want to define what's a kind of a model for two things which are independent. It's there are many kind of models. We studied a huge number of models for one random variable, right? But not so many models for many random variables. And so we can convert models with one random variable to the model with several random variables if we assume that they are independent. So here's an example of what I'm talking about. And so here's example. So so x and y are two independent random variables which are Poisson, say with parameters lambda and mu respectively. Okay, so kind of so 1x is a number of accidents on one road, and Y is the number of accidents on the other side of the United States, and kind of on the other road, and we have kind of, well, we're probably independent. So we're distributed as a Poisson. In one region, it's parameter lambda. In another region, it's parameter mu. So now we want to model these two random variables. And so this is easy to do. Kind of what I mean by model is that we need to write down a joint PMF. So describe these two random variables. And so we write the joint PMF. So joint PMF. P, X, and Y. It depends on two things, X and Y, right? And we write down in them. It's just a product of the individual PMFs. Individual PMFs for this X and Y. So it will be equal. So we'll need to remember what's the definition of the Poisson PMF, and it's e to the power of minus lambda. And so this is for X. So X. So lambda to the power of X divided by X factorial. Right? And we multiply it, so multiplied by, so this is multiplication, E minus mu, mu to the power of Y, right? So it's now Y divided by Y factorial. And here's, so here X can be 0, 1, 2, and so on. Y can be 0, 1, 2, and so on. And so this is just kind of when I say that X and Y are two independent random variables, which are Poisson with a given parameter, I totally describe what's their situation. And so I can write down their PMF. And so maybe kind of a special case. So kind of this is a so it's example. So say if we have a lambda is equal to mu to equal to 1. So suppose it's one accident per day or something like that. We describe the situation. Then there are two Poisson random variables with parameters 1 and 1, with a mean 1 and 1. And so this specializes to pxy of xy equal to e. So here's e minus 1, here's e minus 1. Okay, so it will be e minus 2. Right? And here will be lambda to the power of x. Lambda is equal to 1, so 1 to the power of x is always 1, right? So we can ignore this lambda. Okay, so it will be 1 divided by x factorial. And also, since mu is also 1, we can ignore this 1 to the power of y. So we'll get here 1 divided by y factorial. Okay, so we'll get this thing. So x is equal to 0, 1, 2. Y is equal to 0, 1, 2, and so on. And so if you kind of want to visualize this situation, then we have this picture. So we have here's x, here we have y, and this is infinite table in this case. We have a table here 0, 1, 2, 3, 4, and it's to infinity, right? So kind of here's also 0, 1, 2, 3, and it also goes to infinity. Right? And the entries here will be, so everywhere here will be e minus 2, right? And here will be multiplied by 1, 0 factorial divided by 0, 1 divided by 0 factorial, which is 1. So here will be also e minus 2. Right? So divided by 0 factorial divided by 1 factorial. So kind of it's e minus 2, it's kind of, so because the factorial is always equal to 0. So 0 factorial is equal to 1, factorial is equal to 1. Right? So, but here will be something slightly e minus 2, 1 divided by 2 factorial. Here will be e minus 2, 1 divided by 2 factorial. Right? Here will be e minus 2, 1 divided by 2 factorial, 2 factorial. Right? So here's something by symmetry, right? So e minus 2 divided by 1 divided by 2 factorial. So something like here, kind of, it's by symmetry, the same thing. And say, so if you have something, what's the entry here? Right? So this will be e minus 2, 1 divided by 3 factorial divided by 4 factorial. And so this is big table, kind of, right? And every entry is determined by this formula. And so if you want to calculate some probability, then it will define some region in this table. Right? So, and we'll need to figure out what's the sum of probabilities kind of in this table. All right, so this is an example, hopefully very clear, kind of. So what's the independence means? So just a product. Right, so now, okay, so now we are going to go into more theory. So so this is a important concept, it's a simple concept. And so about simple concept, it is possible to prove some results because they are simple, kind of, right? So, but very important, kind of simple things are most important, right? So here's a theorem. Theorem number 1, it says so that if random variable x and y are independent, and x and f and g are some functions. Functions really doesn't matter much about these functions at this stage because we are live in a very simple world when the x and y discrete random variables. So just arbitrary functions which maps R to R. So from real numbers to real numbers. And then f of x. So we have defined a new random variable which is a function of the previous one, and g of y are independent. And this is more kind of pretty natural. It maybe kind of I even skip the proof of this thing. This is important, very important theorem. But it's so natural, it may be kind of so if you want to just look it up in the kind of lecture notes. So it just says that if you learn something about f of x, so f some functions is square. So if you learn something about square of x, right, and x doesn't give you any information about y, then this function square of x also doesn't give you any information about y or about any function of y. So it's more or less trivial thing, kind of, but you need to prove it. So if you want to see the proof, you can see the lecture notes. So now, well, kind of, so another kind of theorem, so theorem, which one, another theorem which is important, maybe I'll give a proof of this one. It says that its expectation of a product of two random variables is equal to product of the expectation. But if they are only if they are independent, not only, but if they are independent, then this is true. So if x and y are independent, then expectation of x and y is equal to expectation of x multiplied by expectation of y. And this is not true in general. So this is we know that the expectation of a sum is always equal to the sum of the expectation for any random variables, dependent or not dependent. But for the product, it's only true if they're independent. Well, it might happen by accident in other cases, but generally it's only true that they're independent. So, but before kind of looking at the proof for this theorem, we also need to say what's actually what's the meaning of expectation of x times y. So, well, we know how to calculate expectation of x because it's one random variable. We know how to calculate expectation of y. It's also one random variable. We kind of talked about how to but what about expectation of x and y? It's expectation of a function of two random variables. So, so what is the e of x of y? So what is by definition? So in general, so if some z is equal to a function of x and y, so it's function of two random variables x and y. So then, in principle, you can do it by definition. So you'll need to calculate what's the PMF of z. So and so kind of you can calculate kind of this function. So this is a PMF of z. So you can calculate it. So by definition, it's probability that random variable z large is equal to this z small. So z small. And in principle, well, kind of okay. So let me write it's just simply z small. In principle, I probably need to write z kind of calligraphic z. And so then in this case, kind of, so just by definition, so expectation of z is equal to the sum of z small multiplied by the probability of z small, right, over z. But it's kind of, well, kind of, you need to calculate what's the kind of these probabilities, all these probabilities. It's difficult, kind of, we will talk about how to do it later in the course. It's not so easy in general. So we can, it turns out that there is a simpler way to do it. It's just kind of generalization of a theorem that we did before. So simpler way to calculate E of z. It just kind of write it this way. So we say that E of z is actually equal to the sum of f of x small, y small, multiplied by joint PMF, so px y, x y small, and sum of all x and y. So kind of, so this is kind of, this is in principle, this is a theorem that you can do this kind of. So if you define the expectation in the normal way, so that it will be equal to this thing. But it turns out that it is possible to prove it, similar to what we did before. So kind of, so you can use this formula as a kind of definition. It's much easier. So and so if we apply it to the our situation, how to calculate expectation of a product of two random variables, then in this case, what you'll get that expectation. So it's kind of an example. So what you'll have that expectation of x, y, so product of these two random variables is just equal to the sum of the x multiplied by y multiplied by the joint probability x, y, x, y. Sum of all x and y. And after that, you are stuck in general, kind of, right? So after that, you kind of, okay, so this is just some sum. So, well, kind of, you can calculate with sum, but nothing else. So in the case when it's independent, you see that here you can factorize this joint probability, right? So it's a product becomes so. So if x and y are independent, So then, so you can continue this formula. You can start to write that this is equal, so it's equal to the sum of x, y, here's x, y, and instead of this joint, you write a product of two marginals, px of x and p y of y. Right? And after that, you're saying, okay, so what is written here? It's something like that. If it would be 2x and y, right? So it would be just kind of, if it would be something like, you would see that something like that, if the sum looks something like that one. So x1, y1 multiplied by p x of x1 multiplied by p y of y1 plus x 1 y2 multiplied by px of x1 py of y2 plus x 2 y1 px of x2 multiplied by py of y1 plus x2 y2 px of x2 py of y2, right? So this is like that. So it just kind of it's a sum of all possible x and y's, right? So here I denoted them x1 y1. It's one possible value of x and y. X1 y2 kind of, right? It's another combination. So use just sum of all possible combinations. And then after that, you notice that you could write it like that. So it's equal x1 px of x1 plus x2 multiplied by px of x2 and multiplied by y1 of p y of y1 plus y2 multiplied by py of y2. Right? So kind of it's, if you compare, it's the same thing, kind of, right? So it's just a product of these two factors. And in general, you can write that this is equal to sum of x of px of x multiplied by the sum of y of p y of y. Okay, so this is just generalization of this identity. Okay, so which is kind of recognized that this is expectation of x multiplied by expectation of y, by definition of this expectation. Okay, so this is the proof of this theorem. Yeah, so the essential step was here, this thing, right? So if it's not independent, you cannot do this step. Okay, so all right, so this is a super important principle, super important fact about the independence. That okay, so average of the product of two random variables is equal to the product of the averages, and so we have two theorems, and in mathematics, if you have a kind of several results, you can combine this result and get something more stronger. So if you combine it, these two results, then we'll get another thing. So another theorem, which is even more powerful, which says that if x and y are independent, then E expectation of f of x multiplied by f of y. So g of y, sorry, kind of say g of y. Okay, so f and g, as in the first theorem, are just some two functions, right? So I skip this in this formulation. So it's equal to the product expectation of f of x multiplied by expectation of g of y. Right. So kind of, right? So right, so it's much more than you can say. So maybe example kind of. So example. So if you have something like, if you want to calculate what's the expectation of x squared divided by y cubed, then you can write that this is expectation of x squared multiplied by expectation of y cubed. Right? In general, it's not true. Kind of, if it's not, we are not independent, random variable are not independent, then you cannot write it down. But if we are independent, this is kind of true. And so it's the important fear that this random variable are independent. Okay. So now kind of this is now the time is a good time to prove the things which are used many times before, right? Which is concerns the moment generating function, and also another fact was about covariance. But the moment generating function, I said many times before that if you have a independent random variables, now we know what it means, then the moment generating function for the sum of them, the sum of these two random variables, is equal to the product of the moment generating functions for individuals of them, right? So, and we use it to derive many results before. So now we can actually prove it. So this is a theorem which says, so if x and y are independent, then moment generating function of the sum of them. So it's a sum, not a product. We are talking about sum x plus y of t. It's equal to m of x of t multiplied by m of y of t. So his m of t is mgf. So so it's moment generating function of a random variable. So this is kind of theorem, and it's the proof. It's easy once you have this previous theorem. So the proof says, okay, so what's the definition of the MGF? So m of x plus y of the t, it's by definition it's expectation of e to the power of a random variable. Here's random variable x plus y, e to the power of x plus y multiplied by t. T is just some number, some parameter, right? So this is definition. So this thing. Right? And after that, we're using the properties of the exponential. We are saying that this is exponential of the sum xt plus yt. So we can write that this is expectation of e of xt multiplied by e of yt. So just properties of the exponential function. So, okay, so now we observe that here we have a product. And one is a function of the random variable x, another is a function of the random variable y. So, okay, so you can use the previous theorem, which says that the product of two functions of independent random variables. Right? So it's equal to e expectation of e xt multiplied by expectation of EYT, but this is MGFs of x and y. So it's equal m of x of t, m of y of t. Right? So this is all the proof of this. Okay, so now kind of that's it, kind of. So this is important theorem is proved in this way. So now kind of another theorem which I think that I said we used before kind of in some calculations, it says that in general expectations of the sum of random variables, it's also always equal to expectation, right? So we always have that expectation of say x1 plus x2 plus so on plus xn is equal to e of x1 plus e of x2 plus so on plus e of xn, right? So for arbitrary x1, xn, arbitrary means that we are not necessarily independent, right? So just any kind of random variables. Right? But in general, it's not true that the variance. So variance of x1 plus x2 plus so on plus xn, in general, it's not equal to the variance of x1 plus variance of x2 plus variance of xn. Okay, so it's not equal. It's so in general, it's not equal. Right? In general. So, but if x1, x2, xn are independent, then equality holds. So this is true in general. Right? Okay, so now, but this is a many kind of random variables which are independent. So, well, we define it not just for two. Kind of everything can be generalized, of course, but let us prove it for two random variables. That kind of the sum of variance of the sum of two random variables is equal to the sum of the variance. Everything can be kind of easily generalized after that. So let us look at the theorem, right? So kind of it says if x and y are independent, then variance of x plus y is equal to the variance of x plus variance of y. Right, so now let us kind of, this is the last theorem, and after that we'll make a break. So, right, so now, so by definition, right, so in this case, just kind of write it. So this is a simple kind of, once we establish these fundamental results about independent random variables and about the product, expectation of a product of independent random variables, everything after that is simple. So here we'll have a right with the variance of x of y, and we use the formula that we have before. It's equal to expectation of x plus y square, so expectation of the square of a random variable minus the square of expectation plus y squared. And then after that, it's just kind of a more or less tedious expansion of this thing. So we write that this is equal, okay, so expectation of here will be x squared plus 2xy plus y squared. On the other hand, will be expectation of x squared, so minus here, expectation fx squared plus 2 expectation of x, expectation of y plus expectation of y squared. So I use the fact that this is equal to expectation of x plus expectation of y and expanded it. And then after that, I'm looking, okay, so it's equal, right, the first thing, so this would be expectation of x squared. This will cancel out, right? So this will cancel out with this thing. Right? So now expectation of y squared will cancel with this thing. So it's also, no, it's not a cancel, sorry. Kind of, I'm saying the wrong thing, so maybe kind of, hopefully it will remove these things. And so we just, it's not cancel, it's we'll need to regroup it, right? So it's equal to, it's equal to e of x squared minus e of x squared. So this is this thing minus this thing, right? Plus 2e of xy minus 2e of x, e of y. So this is this one and this one. Right? And plus expectation of y squared, this one here, minus expectation of y squared from here. Right? And from this we read that this is equal to the first term here is variance of x. The last term here is variance of y. And this term disappears because we know that e of x times y is equal to the product of x over y for independent random variables. So this thing is equal to 0 for independent random variables. Just to prove the expectation of x, y, so is equal to the product of these two expectations before. Right, so that's it. So this is the end of the proof. So variance of x plus y is equal to variance of x plus variance of y if they are independent. All right, so let's stop now and make a short break for 5 minutes. All right, so let's get back, and now new topic here will be covariance. Not sure what happened. So let me do it again. So got lost a connection on this device. Okay, so now I'm back. Okay. And so maybe kind of another one. Okay, so okay, covariance. So, and this is just generally kind of the idea is this is the answer to the question how to measure independence. Maybe not independence, how to measure dependence. Kind of measure independence, kind of not measure dependence. So in general, the random variables are usually not independent, right? But we may try to use to measure the dependence. And now, one thing is that there are many answers, So one thing would be a dependence inherently means that the conditional distribution is different from the marginal one. So we can define somehow the distance between the probability mass functions, and to measure how far is the conditional distribution from the marginal, and how far it is on average, or something like that. So there are many I can give you many ideas how to measure the dependence, and they are used actually in practice in more sophisticated application. But often we need just a very simple measure, super simple measure, how to measure whether the two random variables dependent or not. Right? And this measure is a covariance. It's based on the fact that if a random variable independence, then E of x, E of xy should be equal to the product of E of x and E of y. So, well, we can look at the difference, E of xy minus E of x and E of y. Right? And well, this is called covariance. So it's a covariance of x and y. So it's by definition a covariance. This is definition of a covariance. And so very simple. So in particular, it means so if x, y are independent, then covariance of x y is equal to 0. Unfortunately, it's not true in general. In general, it's not true. So if covariance of x, y is equal to 0, then x and y may be dependent. So it's not true that if the covariance is equal to 0, then they are necessarily independent. Could be dependent as well. So, but it's useful measure. At one, so one fact why it's useful, it's also related to something which we learned before about the variance. So if you measure what's the covariance of a random variable with itself, so it should be different from 0. Well, x depends on itself, right? So then in this case, we will see that it's equal to, okay, so what's by definition? It's E of x multiplied by x, so E of x squared minus E of x multiplied by E of itself. So, right? So it's equal to variance of x. So covariance of a random variable with itself is equal to the variance of x, and we know that this quantity is greater than equal than 0 and equal to 0 if and only if x is a constant. And so in general, kind of this will be positive random variable as it should be. And so we never property of this variance. And so now, what other nice properties of this thing? And so suppose that we look at the covariance of sum of the two random variables. Okay? So kind of x plus y with no, sorry, kind of that's not what I wanted to say. So this is the first property of the covariance. This is the second, and the third one, it gives you the ability to calculate variance of the sums of the random variables. So if you have a variance, so it's a kind of an example. So a variance of x plus y. So we said that if they are independent, the random variable independent is equal to the sum of the variance. But what if they are not independent? And in this case, you write, okay, so you need to write in this case that this is equal to covariance of x plus y, Okay, so this well, kind of no, let us not write it farther than that, but kind of you can see that we might be interested in knowing kind of how covariance of this one sum, how it's kind of with another sum, right? So and this can be so kind of we're interested in how to calculate these things. So right, so we'll need to know a little bit more about the properties of a covariance to calculate it. So now for this we'll say, okay, so another property, so it's a kind of a theorem. Right? So which says that if you have a covariance of ax plus by, and you calculate it with some other random variable z, then it will give you a covariance of x z plus b covariance of y and z. Right? And other way around, kind of by symmetry also you have this thing. So if you have a covariance of z with ax, it's kind of it's trivial with by, then it's equal to a covariance zx plus b covariance zy. And maybe another thing that the covariance is obviously symmetric, right? So kind of covariance zx is equal to covariance of xz. Now, okay, so maybe I will not prove this theorem. It's just kind of, if you're looking at the definition and write down the definition, it's more obvious from the linearity properties of the expectation. Right? But let's look what we can get from this theorem. So if this is true, then we have at this, we can continue this example, right? So we can continue calculation of the covariance of x plus y and x plus y with itself. We can write that this is equal covariance of x plus y with x plus y. Okay, so it's equal, okay, so we expand covariance of x with x plus y plus covariance of y with x plus y. Okay, so because, well, kind of we're using this theorem where we use this thing as a z. Okay, so now we use this theorem again, we'll get this is covariance of x plus covariance of x, y. So this is instead of this first term plus covariance of yx plus covariance of y. And now we look at the covariance xy, covariance of yx. And I said that, well, kind of it's symmetric function. Right? So covariance of xy and covariance of y of x are equal to itself. So we'll say that this is equal to covariance of x plus 2 covariance of xy plus covariance of yy. So, well, covariance x and x is equal to variance of x plus, okay, so covariance of y, variance of y plus 2 covariance of x and y. And so we kind of derive a formula for the variance of the sum of two random variables. And in general, you can see that covariance behaves like a product of two random variables. So we have here something like a covariance of x plus y, x plus y. Right? And we've got something like a binomial formula. Right? So variance is like a square, right, of a random variable x. And covariance like a product here. So here we'll have something like x plus y multiplied by x plus y is equal to x squared plus y squared plus 2xy. And so this is kind of a main property of the covariance, that it behaves like a square. And so more generally, so if you want to see how to calculate the, say, variance of ax plus by. So in this case, what we'll have? So again, so you think about that it's like a product, right? So we write it, this is variance of ax plus variance of by plus 2 covariance of ax by. So it's equal, okay, properties, covariance a squared variance of x plus b squared, maybe here, b squared variance of y plus 2 ab covariance of ax, so covariance of xy. Right? So maybe an example, so some couple of examples. So well, it should be more or less clear how to calculate, but maybe example helps to see. So say variance of say 3x plus 4y plus say 5, and we calculated variance, so variance of this thing, right? So something like that one, right? So what it will be, something like, so you can think about that it's like something like taking a square of this variable.
Yeah. Do you mean covariance after the generally?
Say it again.
Do you mean covariance instead of variance, like for after the more generally?
So here's variance, right? So not quite follow.
Is it gonna be covariance or just variance?
So here's a variance because it's so okay. So even more generally, this will be something like that one. So let me write even more generally before example.
Mm-hmm.
It's so. So here is still variance, right? So here I still calculated something like a variance of x plus y. Why? You can think about this. You can think as something like a covariance of ax plus by with itself, ax plus by. Right? And after that, you are saying, okay, so this is equal to okay. So after that, we are writing this formula. But so even more generally would be something like that one. So I say something like covariance of ax plus by, here's cx plus a dy. Right? Okay, so I want to calculate this. Right? So a, b, and c and d some numbers. Right? So now in this case, I write okay, so what it's equal to. And again, so it's like a product. So it's something like a covariance of ax, cx plus covariance of ax with dy, right? So yeah, take x and kind of plus covariance of by and cx plus covariance of um, um, by, and the last one is dy. Right? So kind of, right? So kind of, so okay, so I expand this kind of like making a product of this thing. So after that, I look attentively at all of them. Right? So another property of the covariance that you can take. So let's look at this one. Another property of the covariance that you can take with A's and C, these are just numbers, kind of, right? So you can take them outside. You can write that this is equal to AC, A times C. Here's a covariance of X and X. Right? But covariance of X and X, it's a variance of X. Right? So kind of, and so let us write here and immediately write what it will be in the next line. It would be variance of X, because it's covariance of X and X. It's kind of, it's, and after that, okay, so now the next one. So this is A and D. You can take them outside. This is just kind of a property of the covariance that if you multiply one of them by one of the arguments by a number, then this can be taken outside. Will be AD here multiplied by covariance of X and Y. Right? Here, same thing. So here B and C, so it's BC, but okay, covariance of YX. Right? Okay, so covariance of YX, but it's the same thing. So there is also symmetry property. Right? So many properties, so kind of difficult to list all of them. Right? But they are more or less the same as a product. So here will be AD plus BC, here covariance of XY, because these things are the same. And there is a the last one here is covariance by dy. So we have a b and d, we can take it outside, we'll get the covariance of y here. And so it's equal to bg variance of y, because covariance of a random variable, we would say it's a variance, covariance, right? So this is maybe kind of more general property, but it's just for two variables. But you can see that how you can generalize it for many more variables, right? So just kind of by linearity. So there is no independence here right now. Just kind of just. So all right.
Thank you. Okay. Thank you. That makes sense.
Yeah. So one more thing that maybe kind of should be mentioned, kind of, right? So kind of several properties that I use, kind of, and not stated, kind of. So kind of covariance of xy is equal to covariance of yx. Right? So kind of also can be. So another thing which is very useful, that the covariance of x and some constant, right? So it's equal to 0, right? So well, kind of. So well, kind of. Again, so can be checked. Right? So covariance of x with some constant thing. So kind of it's kind of not dependent. So now, and maybe kind of an example. So he want to give us some example, maybe kind of even more complicated example. So maybe covariance of, so maybe two examples. So one of them is a covariance of 3x plus 4y minus 5 with the x minus y plus 1. So I want to calculate this thing, covariance of these linear combinations of random variable. So first thing to say, kind of, okay, so totally ignore the constants. They don't matter, kind of. So the constants here with minus 5, when you expand it, the covariance of something with this constant. But we know that covariance of x with the constant is always 0. They kind of, you learn constant, you don't learn anything about x. So, and this is a properties that can be checked, kind of. So E of x c, it's equal to E of x E of c. And so it's just kind of the random variable and any constant are independent, something like that. So this is kind of the same thing. So it's equal to CEX. Now, okay, so we will continue. So this is an example. We continue that this is equal to covariance of 3x plus 4y, minus y, ignore minus y, with x minus y. So first thing that I did, I forgot about the constants because they don't matter. Right, so in the calculation. So after that, I write kind of, right, so thinking about it like a product, right? So I'm saying, so here 3x and x. So I put in here 3 covariance. So, well, I should write immediately variance, right? So, but kind of for clearness, let me write covariance, f of x of x. Right, so 3, and the coefficient here was 1. That's why kind of it's 1. So next one is 3x and minus y. Okay, so I write it minus 3 covariance of x, y. It's from 3x and minus y. Next one is 4y and x. So I'm writing this as plus 4 and writing here is covariance. In principle, well, I can write it yx, but it's kind of, it's the same. Covariance x and y and x, it's by this property, by symmetry. Kind of they're equal. Right? And the last one is from 4y minus y. So it's minus 4 covariance of y. Right? So, well, okay. Yeah, so now it's equal to 3 variance of x minus, okay, so what here, plus covariance of xy, just because from here and here these two things are equal to each other because covariance of xy is equal to covariance yx, so it's, and minus here's 4 variance of y, 4 variance of y. Okay, so that's the answer. If I gave to you what was the variance of x and variance of y and the covariance of x and y, you could calculate this thing, right? So right. And okay, so this is another kind of example. Maybe kind of this is example for covariance, calculating covariance of the two things. So what about the variance? So what, suppose I say variance of 3x minus 4y plus 1. And again, so the first thing to say, okay, so the constants doesn't matter, kind of. So it's equal to variance of 3x minus 4y. Forgetting about this plus 1, it doesn't matter. And after that, we're thinking about, okay, so, well, you can immediately kind of write it down, but you can, if you kind of, so kind of, you want to kind of to see what's happened, so it's equal to covariance of 3x minus 4y with itself, 3x minus 4y. And after that, you're writing, okay, so it's equal to covariance 3x with 3x, so it's equal to 3 times 3 covariance x and x. So instead of covariance x and x, I immediately write that this is equal to variance of x. So this is from this term. Because I'm skipping this step here, writing the covariance x and x. I skipping this step and writing instead of covariance of x and x, I immediately write variance of x. And after that, you'll have here, okay, so covariance, so it would be something like a minus, okay, 3 times 4, so 3 times 4 covariance of x, y, but will be twice kind of, so it's like a kind of square, it's taking a binomial formula. So will be also covariance of 4y and 3x, so maybe here's another side, 2. It's because there is another term. Next one will be minus 4y times 3x. It will give you the same number. And plus here 4 times 4 covariance of y and y, so variance of y. Again, so maybe kind of kind of a skip here. So we can repeat it without skipping. That will something like a 3 times 3 covariance of x. Here will be minus 3 times 4 covariance of xy, minus now 4 times 3 covariance of xy, and plus 4 times 4 covariance of yy. So this step is, well, maybe should write it down, right? But in principle, well, you can do it all in kind of, well, okay. So this should be clear, right? This is kind of it's essentially what you're doing the product. So kind of if you would do this something like the only thing that you're ignoring is plus 1. If you write the product, so if you write what is 3x minus 4y squared, and you would immediately write that this is equal to 9x squared minus 12xy. 2 times 12xy plus 16y squared, right? So kind of well, instead here will be the same thing, except here will be 9 variance of x minus 2 times 12 covariance of xy plus 16 variance of y. You can immediately see that this is, well, kind of very kind of clear analogy of taking the product and calculating the variance of this. Well, here's a square. It's the same like calculating variance. The only thing that you need to remember that in the variance of anything with the constant is equal to 0. Covariance of anything with the constant is equal to 0. And so it's kind of useful to immediately to remove this constants from the beginning. So they wouldn't be kind of in your way after that. So this is kind of similar calculation. All right, so this is maybe practically the most kind of useful thing, because it allows you to calculate the covariances and variances of many things. So this is a useful thing. So you'll have a couple of these problems in the homework, and this is a typical problem for exams. So you should probably learn how to do it. So, but it's easy thing. So. All right, so maybe we'll stop now. We will talk more about the covariance next time. So we still have not covered all the properties of the covariance. And we will talk next time about a variation on the covariance, which is called correlation coefficient. All right, so okay, so why it stopped again? All right, so okay, so if have question, ask me questions. If not, well, kind of see you on Wednesday.
Good day, Professor.
Yeah, you too.
Thank you.
Thank you, Professor.
Yeah. Thank you.
Thank you, Professor. Have a nice day.
You too.